Hey everyone, welcome. Today we're looking at a Leetcode problem called Find Numbers with Even Number of Digits. It sounds simple enough, and it is. We'll break down exactly what it's asking and look at a couple of neat ways to solve it. Let's dive in. Okay, so what's the goal here? We're given a list, an array, of whole numbers, like 12, 345, 6, and so on. Our job is to count how many of those numbers have an even number of digits. So, 12 has 2 digits. That's even. 345 has 3 digits. That's odd. 6 has 1 digit. Odd again. We just need to go through the list and count up the ones with an even number of digits. The constraints tell us the list won't be ridiculously long, maybe up to 500 numbers, and the numbers themselves won't be bigger than 100,000. Pretty straightforward, right? Let's walk through the first example they give us. The list is 12, 345, 2, 6, and 7,896. Okay, first number, 12. How many digits? 1, 2, 2 digits. Is 2 an even number? Yep, so we increment our count. Our count is now 1. Next, 345. That's 1, 2, 3 digits. Is 3 even? Nope, it's odd, so we don't change the count. Next is 2. That's just 1 digit. Odd. Next is 6. 1 digit again. Odd. Finally, 7,896. Let's see. 1, 2, 3, 4 digits. Is 4 even? Yes, it is. So we increment our count again. Our count goes from 1 to 2. That was the last number, so our final answer is 2. See? We just check each number and count the ones with an even digit count. So the core of the problem is figuring out how many digits a number has. How can we do that? Well, one really straightforward way is to just convert the number into text. You know, like turning the number 123 into the string. Once it's text, most programming languages let you easily find its length. The length of the text is 3, which is exactly the number of digits. Alright, here's how that string conversion idea looks in Python code. We start a counter at 0. Then, we loop through each number in the input list. Inside the loop, the first thing we do is turn the current number into a string. Then, we get the length of that string. We use the modulo operator, that %, to check if the length divided by 2 has a remainder of 0. If the remainder is 0, it means the length is even. And if it's even, we increment our counter. After checking all the numbers, we just return the final count. Let's break that down just a bit more. We initialize our answer, our count, to 0 before we start. Then the for loop says, for every single num inside the list called nums, do the following. What do? We create a string version s of the number num. Then we check, is the length of s perfectly divisible by 2? That lens %2 == 0 part asks exactly that. If the answer is yes, we increase count by 1 using count plus = 1. If the length is odd, we just skip that step and go to the next number. Once the loop finishes visiting all numbers, we return the final value of count. Okay, what if we don't want to convert to strings? Can we do it with just math? Yes, think about how our number system works. If you have a number like, say, 7896, and you divide it by 10 using integer division, where you drop any remainder, you get 789. Divide by 10 again, you get 78. Again, you get 7. One more time, you get 0. How many times did we divide? 4 times. And guess what? 7,896 has 4 digits. So we can just keep dividing the number by 10 and count how many divisions it takes until the number becomes 0. That count is the number of digits. And here's the code for that division method. Again, we start a counter, even_digit_count, at 0. We loop through each num. Inside, we initialize a digits counter for this specific number to 0. We use a temporary variable temp_num so we don't mess up the original num. Now the while loop keeps going as long as temp_num is greater than 0. Inside the while loop, we perform integer division by 10. That's the == operator, which effectively chops off the last digit. Each time we do this, we increment our digits counter. Once temp_num hits 0, the loop stops, and digits holds the total number of digits. Finally, just like before, we check if digits is even using the modulo operator, and if it is, we increment our main even_digit_count. After the outer loop finishes, we return the total. Let's look closer at the core logic here. For each number from the input list, we first set a local counter digits back to 0. We make a copy temp_num just to be safe. The while temp_num greater than 0 condition means keep doing the stuff inside as long as the number hasn't shrunk down to 0 yet. Inside, temp_num /=10 is the key. It divides the number by 10 and throws away the remainder. So 123 becomes 12, then 1, then 0, and digits plus equals 1 just counts how many times we successfully did that division. When the loop finally finishes because temp_num became 0, digits holds our answer. Then we do the familiar check. If digits %2 equals 0, and if true, we bump up the overall even_digit_ count. Here's another math trick, a bit more advanced but quite elegant. It uses logarithms, specifically the base 10 logarithm. There's a neat property. If you take the base 10 logarithm of a positive number, take the of that result, which means just chop off the decimal part, keeping the whole number, and then add 1. You get the exact number of digits. For example, log base 10 of 7,896 is about 3.89. The floor is 3. Add 1, and you get 4. Magic. Well, math magic. So we can use this formula to find the digit count directly. Okay, here's the code using the logarithm approach. We need to import math first to get access to the logarithm function. As usual, start the count at 0 and loop through the numbers. Inside the loop, we calculate the number of digits. We use math.log10 num to get the logarithm, math.floor to chop off the decimal part, and then add 1. We store this result in digits. Then, just like in the other methods, we check if digits is even using digits %2 equals 0, and increment count if it is. Finally, return the count. Note, we add a little check if num greater than 0, because logarithm of 0 isn't defined, but the problem constraints guarantee numbers are at least 1, so it's mostly for completeness. Breaking down the logarithm part. First, make sure you have import math at the very top of your file. Inside the loop for each number, we apply the formula. Math.log10 num gives us the logarithm. Math.floor takes that result and removes anything after the decimal point. Then we add 1 to get the actual count of digits. We store this in the digits variable. The rest is the same logic we've seen. Check if digits is even with digits, %2 equals 0, and if so, add 1 to our overall count. It's a very compact way to find the number of digits using a built-in math function. So how efficient are these methods? Well, notice that in every approach, we have a loop that goes through each number in the input list nums just once. Let's say there are numbers in the list. Inside the loop, we do a little bit of work to count the digits. Whether we convert to a string, use division, or use logarithms, the time it takes depends on the number of digits in the number, not how big the number itself is. Since the numbers are capped at 100,000, which is 6 digits max, this inner step is very fast and roughly constant time. Therefore, the total time complexity is dominated by that single loop through the list, making it big O of n, or order n time. What about memory? We're only using a counter variable, and maybe a temporary variable or two inside the loop. We're not creating large extra data structures. So the extra space we use is constant, which we call big O of 1 foot, or order 1 foot space. All these methods are very efficient. So let's recap. The problem was simple. Count the numbers in a list that have an even number of digits. The key was figuring out how to count those digits. We looked at 3 solid ways: turning the number into text and checking its length, repeatedly dividing by 10 until the number hits 0 while counting the divisions, and using the neat math trick with base 10 logarithms. All of these approaches work well and are efficient, running in time proportional to the list size, order n time, and using minimal extra memory, order 1 foot space. Pick the one you find easiest to understand. Hope that breakdown made sense and helped you understand the problem and its solutions. If it did, feel free to hit the like button, maybe subscribe for more Leetcode explanations, or leave a comment if you have any questions, or perhaps another cool way to solve it. And hey, if you're feeling extra awesome, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.